Thank you very much, Bronwyn, for your introduction. As we can see on the date on my title slide, I would have preferred to give it actually a bit earlier in the conference. Never mind, 15th of October, I put it. Okay, so time-dependent infrared spectroscopy is quite a common tool in polymer chemistry, and in our laboratories we have employed it to study the release of solvents from a few gels that can be used for the surface cleaning of paintings, and we have done this by studying the diffusion in model systems of oil paint binding medium. And these model systems, I think it's best to first go into detail a little bit about their composition. So they are based on linseed oil, which can schematically be depicted as a triacylglyceride with, these one or two double bonds that those have the possibility to cross-link with oxygen and form a tightly cross-linked polymer network. And in this case, we have chosen to introduce metal ions into the network by cross-linking a zinc carboxylate compound, or in lead carboxylate compound, and in that case, introducing metal ions, creating a network that is similar to an aged binding medium. However, it doesn't contain any pigment. And the reason is to choose such a model system is that it's good for systematic studies because you have a known concentration of metal ions in your system. And you can see here also on the bottom right how this looks in real life. So on infrared spectroscopy, we see on the left, the red spectrum is our zinc carboxylate molecule that is basically cross-linked into the network. Upon heating that with linseed oil, you can see that it disappears and you form this zinc carboxylate group that's characteristic for aged zinc paints. It's very similar to what you get when you mix zinc oxide with linseed oil, which is depicted in green. And the only difference that you see here basically is the absorption of zinc oxide at very low frequencies. In XRD, we see that we have a completely amorphous system, having scattering in all directions, such as liquid. This is basically what you would also obtain if you would take an XRD spectrum of just linseed oil. So no crystalline material in this system. And this is the model system that we used to test the release of solvents. So for this solvent release test, we developed a cell, and it's schematically depicted here. On the left, we see the design schematically. It's basically a solvent reservoir where you can load it with a solution with a solvent, and from the top, the solvent penetrates through a porous metal disc that is with a light pressure. It pressurizes your model system onto the infrared detector. And, in analogy to that, we can, instead of having a reservoir of solvents or water, we can also have a reservoir of solvents or water in a gel. And in that case, we have the situation that's depicted on the right. So solvent diffusion in infrared spectroscopy, how does that work? Well, you have a certain infrared vibration that's associated with characteristic for a solvent. And at time 0, you don't see any solvent at your detector. However, when the solvent starts diffusing into the system, you see that these characteristic bands are growing, and you see basically how you see the picture on what's exposed here. And by doing an integration of this band, one can obtain a concentration profile for the solvent in the polymer. I call it polymer. We can call it paint as well, but it's in this case no pigment. Assuming Fickian diffusion, this data can be fitted with a mathematical model for diffusion, and that allows you to extract the diffusion coefficients for certain solvents. And just as what we can use this system to obtain the diffusion coefficients, it's also possible to obtain information about the swelling of your system, because basically what you have is a system that you have a measurement volume, and into this measurement volume, in the beginning you don't have any solvent present. However, as soon as the solvent starts diffusing, the measurement volume is filled up with solvent, and the effective concentration of your polymer goes down, which is a measurement of the swelling. So, having established this method, it was decided to test a wide range of solvents that are used for the cleaning of paintings, and we obtained for zinc and for lead model systems very similar results. These concentration profiles span a wide range of diffusion speeds. So if you look at the bar chart, this basically just depicts the same information as the concentration profiles. So in red we see the diffusion coefficients, and in black the swelling. And it's evident that generally high swelling solvents also have a fast diffusion. However, alcohols have a relatively high swelling compared to the diffusion. And it's these results are also obtained by other researchers in the past with different techniques, and it's nice that they agree well with trends that are found in literature, because this means that we have basically developed a method that works well for measuring diffusion in paints. And we can also do this for gels. So in this case, these are the diffusion or the concentration profiles of water that is released by a selection of gels. In this case, we have gels from Nano Restart, 2 of the Peggy gels from Nano Restore, and 2 agar and gelen, so polysaccharide-based gels. And it's in this case you see again the bar chart in gray depicted is the time that it takes for a solvent to diffuse through the layer, and before it's basically detected at your infrared detector. So that's this time. This is depicted in the gray charts, and in the green bars is the diffusion coefficient. And this is compared to solvents or water diffusing from a reservoir of solvents compared with diffusion from a gel. And in some cases, because we don't have a very large sample size, there's a small reduction in either retention or diffusion. But for all practical purposes, these results show identical results for free water and for all the gels. So how can we explain that? Well, we have in this case a complex interplay between the diffusion out of a gel and the diffusion into the paint. In this particular case, we have the situation that the diffusion out of the gel is much faster than diffusion into a non-porous model system of oil, and therefore we get accumulation of water at the interface of the gel and the oil, and this gives a result that explains basically how the results for a release from a free water and water confined from a gel are so similar. And we expect that in more porous systems this would show different results. So with that, I would like to conclude that we can use infrared spectroscopy to study time-dependent infrared spectroscopy to study the transport of small molecules in paints, And in this particular case, where we have a non-porous model system, the gel determines the diffusion, and not the gel. The paint surface determines the diffusion, and the gel does not. So gels can in this case be used for controlled application of solvents. You can specifically apply them at a specific spot, but we cannot control the release because these systems are relatively non-porous. And we expect that in highly porous systems or with short application times, this might be possible. So with that, I would like to acknowledge my colleagues, Piet, Katrien, Joen Hermans, and all the partners in the project that I'm working. And I would like to kindly thank you for your attention.